addition stuff. It's not a must to know, but it's actually quite cute. So all this is saying, you would have seen this symbol before. It's capital sigma, and it stands for addition. The sum means sum of, right? And it's saying starting at 1, so when I is 1, the first term, I better write this, the first, oh, I don't know why they're always slanty, never mind. So you probably should be writing this. So what this means is we start with 1. When I is 1, we have 1. The next term, when I is 2, is just going to be 2. When it's 3, it's 3, and so on. So when I'm adding up all of these terms and I go all the way up to n, what it should do is this will be n plus 1 over 2. And what we are wanting to do is now we want to prove this. So does everyone get what we're talking about here? Like, let's say I said, what if we went up to n is 4? Instead of us having to say 1 plus 2 plus 3 plus 4, which is 7, 8, 9, 10, I could just pop it into this. That is saying that's the shortcut. So that would be 4 times 5 over 2, which happens to be 10, right? Wouldn't that be a hell of a lot easier if I said, oh, hang on, we're summing now for how many terms? 100. You don't want to go 1 plus 2 plus 3 plus 4 plus 5 plus 99 plus 100 equals. We could just put 100 into here, correct? So we do not want to just keep doing it for, 5, 6, 7, 8 values of n. We want to prove it by mathematical induction, correct? So we do the same process that we did before. What is it that we have to do? First step. We write Pn. So here's my Pn. And we better go, what was it? N is all positive integers. So n positive integers, and I can get rid of that because I don't need that anymore. Agreed? Right, what was the next thing that we did? Or have to do? Right, we want to prove P1. So on the left-hand side, the first term is 1. On the right-hand side, we've got 1 times 1 plus 2 all over 2. This equals 1. So therefore, P1 is true. Do I have to write P1 is true? Yep, yes you do. What's the next step? Assume PK is true. And you basically just go back to the original thing that we've got, and wherever n is, you just replace it with k. So we're not doing any thinking. You could be having a good old gas bag and you're just copying. Well, actually don't do that because you could make a mistake and then that's not good. Right, all we've done is rewrite and we're copying it out, like seriously. And I'll just stop because people are copying. Keats is telling us every single time, right? Peeps, you know this, let's participate. Get into it, right? So well done, Keats. We are going to say to prove PK plus 1, right? And that one is 1 plus 2 plus 3. Now, Charlotte, you were just asking, do you have to write that all the time? When we do this, I like to say plus k and then have my k plus first term. Just, I don't know, I just like it. Makes the substitution of k, pk, that much easier to see and sensible. So it is now only at this point that we actually start, well, I wouldn't even say this point, because we know the next step every single time is here to here. What is that? That is actually PK, agreed? Is lamb in the house? So my left-hand side suddenly becomes k plus 1 all over 2 plus k plus 1 using pk. And so it's only now that you sort of have to do some maths to try and make this look like the right-hand side. You can see very clearly, good Rian, that they are different fractions. We want to make it a single fraction, so he said cross multiply, so that's right, that's over 1. We get a common denominator of 2, so this is now k plus 1. I have to times this by 2, so I now get 2 lots of k plus 1. And again, I appreciate your copying down madly. And you've got 2 options at this point. Now, you could expand and then factorize, but what you should always try and do is ask yourself, always, is there a common factor? Is there a common factor? Yep. Absolutely. What's my common factor? K plus 1. So k plus 1, k plus 1. I'm going to pull that out. And lo and behold, I'm left with the k plus 2 all over 2. Now, this is where we have to be really careful. You have the answer up here. You want to make it really crystal clear to the marker that you understood why you went from here to here, that you didn't just go, oh, I've got no idea, I'm just going to write down the right-hand side. Okay, so just to make sure that the marker's not going to go, yeah, you didn't know what you were doing, you're just copying down the right-hand side, just put common factor. Even underlying it, that would help. Equals the right-hand side. We are making sure that we say, therefore, pk plus 1 is true, and we finish it off by the statement. Anyone want to do the, who would like to say the statement? I'm walking around. I know you can do it. Where am I stopping? Should we go all the way to the back? Should we get memento of Nayato on?
Momentum.
A memento when you leave us. We can always sit back and listen to this one day. What do you like to say to us?
Thank you.
You're so sweet. You're so sweet. Now, Harush, what's the statement, mate?
pk plus 1 is true.
Oh. We have to go right back to the beginning. What was the first thing we did? Since
pk is true.
Nope.
Since p1 is
That's
true.
the way.
Since p1 is true.
And we prove that pk plus 1 is true.
Yep.
Whenever pk is true.
Yep.
Therefore, pn is true for all n is z by mathematical induction. Correct? All right. So, ideally, what I would be saying is write that statement out every single time. Because then when it comes to, you don't have to go, oh, what was it? Because remember, you won't be having a notes page. So when we see the notation, remember what this is saying is the first term is when I is 1. So your first term is going to be 1 times 1 plus 1, so 2. Your next one, we say add, and now I is going to become 2. So it becomes 2 times 2 plus 1 is 3. Plus, now I is going to be, so that's when I is 1. This is when I is 2. What's when I is 3? 3 times 4, etc., etc. So we go all the way up to when I is n, so that's going to be n times n plus 1. And they're telling us that this would be the same as n times n plus 1. So, without me, I think you can quite easily go do the P1, do the assume PK, do the K plus 1, and then we'll all meet to see if we can prove the end of it. Okay, so this was part B. We did that, we did that. Shh. All right, who's playing with us here? Dave, did you have success? Did you get to this point? Okay, so all of this we can replace now with K. Do you agree with that, mate? Okay. And don't forget, you have to add on the other little bit there. Chaps at the back, quiet please. So, none of that we've actually done a heap of anything, really. It's just write, rewrite, whatever. And what we want to do, well done, Lamb. What we want to do is make it as one fraction, make it look like this. So we know that this is now over 1, agreed? That's from that bit there. All of that was PK. People are looking at me like I'm got 2 heads, okay? What have I done wrong? Because this is K plus 1, so I replaced this with K plus 1. So I get K plus 1. K plus 1 is K plus 2. We're good? Okay, so I get one common denominator of 3. I don't have to do anything with this, so I just rewrite K plus 1, K plus 2. What do I have to do to the right hand, this bit? Times by 3. And we shouldn't be going, oh, Lord. Oops, shouldn't say Lord. Oh, boy. I don't want to have to expand and then factorize, because what did we always say? Pull out a common factor. What's your common factor, Rian? No, it's not K. It's not just K plus 1. It's K plus 1, K plus 2. Now, unfortunately, I'll tell you now, I think there's one coming up where you do have to expand. But sometimes you don't have to, so always look to see if you can pull out a common factor first. So we're going to go K plus 1, K plus 2, and we're left with K and 3, all over 3. And once again, we're just going to say common factor. That equals your right-hand side. Therefore, P1 is, PK plus 1 is true. And a statement.